Hello everyone, welcome to DS from scratch. Now, in this particular video, I want to talk about a classification algorithm, which is nothing but logistic regression. Using a regression line, we will be classifying the data into two classification. It's a binary classification. So for logistic regression, what we need initially is a line. Okay, a line of y is equals to like w times x plus b, a data which will split the data into two classification, a line which will the data which will classify the data into two classification. So we will be needing this equation for predicting the y values. Okay, so in logistic regression, the y value can be any value, can be 10, can be 5, can be 2, but our classes, as you can see here, is either 0 or either 1. Okay, so we will not be needing these big values. So for that, what is the solution? The solution is basically to bring the values into a range of 0 to 1. So for that, we will be using a function which is called sigmoid. Okay, sigmoid function. Sigmoid function is basically a function which is converting any number of any data with any range to a range of 1 to 0 to 1. So okay, so the formula is 1 over 1 plus e to the power of minus x. So this minus x can be any value. Okay, so in here our minus x value will be the value of the y. So we will give the value to the sigma, then we will change the range to 0 to 1. So finally, for classifying the data into two classification, we will say that if the sigmoid value of y, like if sigmoid, okay, if sigmoid of y is greater than 0.5, okay, it will classify to class 1. Okay, if it is less than 0.5, then it will be classified to class 0. Okay, so this is the main logic behind the logistic regression. Okay, so now let's dive into the algorithm. Okay, so now let's clean it and then dive to the algorithm, which will be using a pseudo code. So everything will be from scratch. We will be coding all the algorithms, everything, gradient descent, and everything will be from scratch. So that's why I want to teach everything from scratch, so you will understand everything better. Okay, so first let's why we shouldn't start by plotting the data, so we will have a better understanding of the how the data looks. Okay, we can features all the row column 0, and features features all the row column 1, and divide the data based on the labels. Okay, so this is our data. The line I was talking to you is this line. Okay, is this line. We have to create a line which should separate the data into two parts. Okay, this line we will be needing, we have to find this line which separates the data specifically into two classes. Okay, so we will be, the main goal of this uh, algorithm is to for finding this line that separates the data. Okay, so as I said, first we need a line equation. For line equation, we need weight and biases. So let's start with initializing the weight. Np dot ones, we can start with any random number. Let's start with ones, or we can start by with zeros also. So features dot shape, the number of columns. Okay, and bias will be only one value. Np dot ones, only, sorry, only one. Okay, so let's have a look into weight and bias. For having the weight and bias, what we can do is we can predict the value. Let's say the initial predicted value is predicted value, np dot product of features and weight plus bias. Okay, so let's have a look to the predicted value through length. Okay, so this is our predicted value, which you can see is it should be 0 0 0 and 1 1 1. Okay, so because that our class is between 0 and 1, but it is bigger than 0 and 1. So what we have to do is we have to change it to a range of 0 and 1. For that we will be using sigmoid function. So let's store the data to yp 1 over 1 plus np dot exponential of minus rate value. And now let's look at the data yp. Okay, so this b should be small. Okay, so now this is the value. You can see that it is between 0 and 1, but the only problem is all of the values are greater than 0.5. So it will uh, classify all the data to first class. So now let's what we have to do is we have to change the weight and bias. So for that we need gradient. Okay, so let's first start with calculating the gradient of the weight, which is equals to np dot okay features features and okay yp minus y okay over length of yp. Okay, so this will calculate as the uh, average error for weight. Okay, now let's have a look to weight gradient. Okay, so name wise, okay, we don't have anything called y, it is all in labels. Okay, okay, this is a shape problem. We have to transpose the features. Okay, so this is our weight and weight gradient for weight w1, gradient for w2. So similar to that we can, and not similar to that but a bit similar to this process, we have to calculate the gradient of the bias, which is equals to uh, yp minus y. Okay, the error between predicted and actual value, we will take the sum of the value and then divided by the length of yp, which will give us the average error which is caused by the gradient. So let's by the bias. Okay, so then let's have a look to b greater than, again the same mistake I have done. I think we have called y, all are stored in the labels. Okay, so now we have calculated the weight and bias. Now we can update our weight and bias. For updating the weight and bias, we can say weight is equals to weight minus, or just simply you can say weight minus is equals to learning rate. A learning rate, and a learning rate you can choose. We can say 0.1 times okay times w gradient, and bias similar to that minus 0.1 times b gradient. Okay, so the learning rate for weight and bias should be the same because their learning should occur in the same rate. Okay, so now let's have a look to the new weight and bias. So this is our new weight and bias. Initially the weight 1 was 1, the weight 2 was 1, and the bias was 1, but now the weight 1 is 0.96, the weight 2 is 0.94, and the bias is 0.95. So you can see that the both weights are not changing in the same scale. So sometimes we need more change in weight 1 than weight 2, or weight 2 than weight 1. Okay, so now we have weight 1 and weight 2. Now we can again predict. So before predicting, let's have a look to how much was our total loss. For calculating the loss of a binary classification, we can use a logarithmic method, which is basically the product of the actual value times the actual value times uh, log 2 of the predicted values. So if our labels are 1, then it will calculate this error. But what if our label is 0? If our label is 0, this term will be 0, and then we can take another term of 1 minus Okay, labels. So in this term, if label is 1, then this term will be 0. Okay, times np dot log 2 of yp, uh, 1 minus y p. This is our loss. So let's have a look to the loss value. So this is the total, the loss for each label. Okay, so we can take the summation of this loss and do the average. So we just need the average loss, how much, like in average, we how much loss we have in each class. Okay, in y p. Okay, so this is the average loss for all the classes 2.20. So now let's so first let's predict the value. We can use again the same equation, breed value. Okay, control v. Now let's take change it to a sigmoid function by p. Now let's have a look to the loss value. Okay, control v, control enter. Now this is the new loss value. The new loss value is 2.10, while the initial loss was 2.20. So in the just in one iteration, we have decreased by zero point 0.1 loss value. If we do this iterations for so many times, for suppose for 100, for 1000, for 10,000, then uh, now imagine how much our loss will be decreasing. Now let's do that for I in range of like max iteration. How many iterations you want? Like we can say 1000, because it is a very small algorithm, so it will complete in a very short time. Now let's do all these things. First of all, we will predict the uh, by value we will predict, then we will convert it to a sigmoid function. Then after that, what we will do is we can calculate the gradient for weight. Okay, we can calculate the gradient for weight, we can calculate the gradient for bias. Okay, bias. Then after that, what we will do is we will change the weight and bias. Okay, this is the change format of weight and bias. After each changing of the weight and bias, will go again to the to this function. Again, it will predict the value. Then again, it will calculate the with gradient and bias. So finally, after finishing the loop, we want to have the loss value. How much is the loss value? Control C, Control V. We want to have the loss value, and we want to convert the values to the actual level. So for that, we can say that in yp is equal to np dot array. Okay, one if, okay, if like suppose p is greater than 0.5, else 0 for p and yp. Like here we are saying that convert any value in yp which is greater than 0.5 to 1. If the value is less than 0.5, then give us 0. So it will give in the output, it will be only two values, either 1 or either 0. So now let's print. First, let's print labels, our actual value, print yp, predicted value, and let's print the total loss. Okay, let's run the code. This is our results. So this is the labels 0000111, and this is the predicted 0000111, and this is the loss value. Now you can see after 1000 iteration how much our loss value has decreased. So this decrease in loss depends on our learning rate, depends on two factors. One is the iteration range, iteration number, and then the learning rate. If your learning rate is small, then you may need more iterations. If your learning rate is a bigger value, you may need a small iteration value. So this is our final output. Now you may wonder how, like, how it looks like in plot, like if we want to plot that line in a plot. So you we can we know that the equation of a line is, like in this case at least, w1 x1 plus w2 x2 plus b is equals to 0. Okay, so now suppose we don't have the value of x1, so we want to say x1 is equal to w1, x1 is equals to minus w2, x2 minus b. Okay, so now we want to divide all the values by y1, so we have only x1, w1. Okay, all the values by w2, so here we cancel, so now we have only x1, which is equals to this equation. Okay, so using this equation we can plot the line. Okay, so now let's go by that. We can say x1 is equals to minus w2, which is w1 in index. Okay, and x2, okay, over w1, which is w0, and again minus b over w0. Okay, in this case let's consider x2 as feature 1. Okay, x2 is equals to feature features all the row column 1. Okay, x1. So this is x1, and we have find it through feature 1. Now let's plot it. Okay, we can say sns dot scatter plot features all the row column 0, features all the row column 1, and classify the data based on our predicted value, which is yp. Okay, so one plot, then sns dot line plot, we can say x1 and x2, okay, which is feature 1. Now let's look at the plot. Okay, so now this is our final plot and final output, which is this line. Okay, so in this line you can see that, okay, the values which are below the line, okay, all are classified as 0, and the values which are above the line are all classified as 1. Okay, so this was the logic and scratch code for logistic regression, which is a very useful tool in real life as well. Not just it is not just a fancy machine learning algorithm. It is a very useful tool in industry also. Like suppose for classifying the emails, if it is spam or not spam, if for classifying for deciding if a bank should give the loan to a customer or not. It is all done by this kind of algorithms, basically this logistic regression algorithm. So thank you for following me. I hope you enjoyed the video and learned something new. If you like the video, please press the button like and subscribe to the channel, so it will motivate me to come up with new algorithms and try to do it from scratch for your better understanding. Thank you so much.